for some pre-lab questions. Some instructors will make you do these before the lab. We're not going to do these. You don't have to do them before the lab. But what you want to keep in mind is that when I was a student at UCLA, we always had pre-lab quizzes. And so these would be questions that are kind of typical of pre-lab quizzes. So what you have to do is you have to read through the experiment and make sure you understand the concepts and calculations and whatnot. And then the first thing that happens is when you go in the lab, you automatically take the pre-lab quiz. That's what we did. But let's take a look at experiment 1B. A water-soluble sample containing an unknown amount of sulfate weighed 0.4892 grams. So water-soluble means it's a solid. So we have a solid sample that contains sulfate weighing 0.4892 grams. And this being a solid, the sulfate is locked into a crystal lattice. And so that's why I write sulfate solid, because it's in a crystal. There are going to be cations in there too, but we don't know what the cations are. When something's a solid, we think in terms of motion, like the ions. If I try to visualize what's happening with the ions, what types of motions can this sulfate undergo? Well, normally when we think about motion, we have 3 types of motion. Does anybody remember the 3 types of motion? Or maybe you didn't cover these, I don't know. All right, Kiana? Yeah. Vibrational, rotational, and translational. So the sulfates are going to be vibrating in the crystal lattice. That's fine. There's definitely going to be vibration. There might not be rotational. Even though sulfate's spherical, it's like a ball, you know, it might have difficulty rotating because it's not a perfect ball, perfect sphere, but sometimes they can rotate. But definitely when we have a solid, there's no translational motion. It's locked. It can't move. And so it's kind of stuck in its place. And then they're telling us it's water-soluble sample. When reacted with excess barium chloride, the sample produced 0.8462 grams of barium sulfate. What is the mass percent of sulfate in the original sample? So what we're trying to do is we're trying to analyze these for percent sulfate content. You know, how much of this 0.4892 grams is just pure sulfate? It can't be 100% because we can't have anion without cation. And there could potentially be other cations present in there. And so let's take a look at this here. Experiment. And so the first step is we need to free up the sulfate. So right now the sulfate is locked in a solid lattice, and we have to free it up. In other words, we have to dissolve it. And dissolving it is not so easy, you know, because if we can dissolve it, that will free up the sulfate. Sometimes these samples are easy to dissolve. Water will do it. And so we could just use water. For our samples, water is enough. But when you get to more advanced classes, water sometimes isn't enough. And so what would you try next? Let's say I tried water, it doesn't dissolve completely, or maybe it doesn't dissolve at all. What could you try next after water? You could try hot water. You know, some things dissolve easier in hot water than in room temperature water. So this would be room temperature, RT. Let's say hot water wasn't able to dissolve it. What would you try next? I'm sorry? Cold water most likely is not going to work. If room temperature didn't work, I probably wouldn't go that route. You know what I'd probably do? I might try something like alcohol. The reason I might try something like alcohol is because of the solubility rules for molecular compounds. So let me talk a little bit about the solubility rules here. And so for molecular compounds, we have this rule. It's simple. Like dissolves like. So the strategy for going to alcohol is it's not as polar as water. And so we're trying something less polar. So we could try alcohol. If alcohol doesn't work, then we could try something like hexane. If I look at hexane, hex, how many carbons is hex? 6. Normally we can write them in a zigzag way like this because all these carbons are tetrahedral carbons. So I'll have the tetrahedral bond angle here. So that's 6. And then I'll fill the rest in with hydrogens. So I'll have a hydrogen up here, here, here. So this is, I'm trying to draw this more three-dimensional. I could flatten the whole thing out, which is fine also. Something like this. And this is what we call non-polar. So the strategy here is going from something quite polar, like water, to something of intermediate polarity, like alcohol or other things, ketones, to something that's non-polar, like hexane. So if I'm trying to dissolve a candle, a candle's not going to dissolve in water. Will a candle dissolve in hot water? Hot water might melt a little bit, but it really doesn't dissolve. Does a candle dissolve in alcohol? Maybe a tiny bit. But would the candle dissolve in hexane? Yes, the candle should dissolve in hexane. And if it dissolves in hexane, then you should be able to evaporate the candle and get the hexane back. And so these are what we call physical dissolution processes. Let's say none of these worked. What else could you try? You could try acid. But acids oftentimes what they do is they don't do a physical, this is called dissolution. What does dissolution mean? Yeah, just dissolving. Just a fancy word for dissolving. Oftentimes the acid will eat things away in a chemical dissolution process. Let's say acid didn't work. Then what would you try? Base. Let's say nothing's working. Then what would you try? Well, it depends on what type of acid we use. Normally we use something like HCl, which is called a mineral acid. Mineral, like HCl, etc. But if the mineral acid didn't work, then what we could try to do is we could try to use a oxidizing acid. All acids are oxidizers. Mineral acids are just moderate in strength. Some acids are quite strong, like HNO3. So both nitric acid and hydrochloric acid are strong acids. Hydrochloric acid is a moderate oxidizer, whereas nitric acid is a strong oxidizer. But we have to be careful because that could lead to a chemical change, and sometimes the chemical change has no impact. Sometimes the chemical change destroys what we're trying to analyze.
I'm sorry if you went over this before I arrived, but why does heat help dissolving? Why does heat help solution?
Why does heat help dissolving? It helps like 90% of the things to dissolve easier because if we increase the temperature, we're increasing what? Temperature is a measure of kinetic energy, and so you just have more violent collisions. The more violent collisions will get things to dissolve. Or so if you have a solid that's not dissolving, heating up might get it to dissolve because you just try to break apart the lattice, the crystals apart, using kinetic energy. If nitric doesn't work, then what do you do? Do you give up? Probably not quite yet. We try hot nitric acid. Hot nitric acid, if that doesn't work, then maybe we'll consider. Maybe it's not going to dissolve. Have you ever tried to dissolve a diamond? No. You probably don't want to dissolve a diamond anyway, but have you ever tried to dissolve glass? Glass is more specialized. Actually, hydrofluoric acid works for glass, the way it attacks it chemically. But we'll continue on here. Yeah, trial and error. A lot of this is trial and error. But you have it easy because the first thing you're going to try is water. And you know what? It's going to dissolve easily in water, so you don't have to worry about it. Let me just... So we take our unknown, and now what's unknown about it? We know it has sulfate. We just don't know how much sulfate this sample has, and we would just want to make sure we analyze this for its sulfate content. So take our unknown solid and then just dissolve this in water. And when we have a sulfate salt, sulfate salts are soluble, except for which ones? So let me go over here, and we're going to talk about the solubility rules for ionic compounds. There are different solubility rules for ionic compounds. I like to use the ones from, I think, Chem 4, and there are 7 of them. So, 1, 2. Does anybody remember the first one? I have a bad connection here. With my tablet. Kiana? Yeah, good. Let's see. Okay, let me just do something here. Group 1, which are the alkali metals, and ammonium. What's the formula for ammonium? Ammonia is NH3, but ammonium is NH4, and the charge? Plus, yeah. So ammonium. Group 1 and ammonium salts are all, yeah. Now, are these solubility rules or solubility laws? Yeah, they're rules. And with rules, there are a lot more exceptions that we expect. So for example, not all group 1 salts are are soluble. There is an insoluble one that I can think of right now. But you might not have ever heard of it. It's sodium uranyl acetate. Have you ever heard of that? Probably never heard of it because it contains uranium ion. So it's not very common. We're not going to worry about it. What about number 2? So first we look at the cation, then we look at anions after that. And the first set of anions that we're going to look for are the what are these? Cl minus, Br minus, and I minus are called just name them. Chloride, bromide, and iodide. These are soluble except for which ones? Actually, no, you know what? This shouldn't be 2. This should be 3. Because there's some anions that are all soluble. Do you know what they are? What anions are all soluble? Anion salts. Nitrates, acetates, chlorates. Nitrates, acetates, and chlorates are all soluble. Again, this is solubility rules. Like there is a mercury salt with nitrate that's insoluble, and lead.
Soluble, like in general, or water?
Oh no, soluble in water. These are just solubility rules in water. When we talk about solubility for both of these, let me define it. There's a qualitative solubility rules. And there's quantitative. So qualitative solubility rules, we have 3 categories. We have S, SS, and I. S stands for soluble. Does that mean it's 100% soluble? Can you dissolve an infinite amount of sugar in coffee? So does that mean sugar is insoluble in coffee? Yeah, only after a certain percentage. And so what is that percentage, or what is that cutoff in terms of concentration? Does anybody know the cutoff? Sugar easily meets this cutoff. The cutoff is it has to have greater than 0.1 what? Mole per liter. In other words, greater than 0.1 molar. And so if it's 0.2 molar, then we call it soluble. But if it's 0.05 molar, we call it insoluble. It's arbitrary, this cutoff. Therefore, we have SS. SS is slightly soluble. So if it's at the borderline, then it's going to be about 0.1 molar in terms of solubility. And then if it's insoluble, that just means it has less than 0.1 molar solubility. And so quantitative is how much dissolves. Actually, how much. And we have different units. It could be grams per 100 milliliters or moles per liter, whatever. And so we have the nitrates, acids, and chlorates. Those are all soluble. And now we can go to chlorides, bromides, and iodides. These are all soluble except, let's just say, I shouldn't say all soluble. These are soluble except which ones? Ag plus. Ag plus is called what? Silver. Pb2 plus. Lead 2 ion. We need the Roman numeral for that one because silver is fixed charge, lead is not. Lead is variable charge. What's the other charge on lead? +4 is correct. And mercury 1. What's the formula for mercury 1? Hg2. How can mercury 1 be Hg2? Can somebody explain that to me? Mercury 1 is Hg2 2+. And so what it is it's a ion, it's a polyatomic ion. You have two mercuries that are bonded together. And so you have to take them as a pair. You can't split them apart. But if you were to split them apart, each mercury would be +1, not +2. If each mercury were +2, the whole thing would be +4. And so that's mercury 1.
Why do two mercury atoms form a bond? What kind of bond?
Covalent bond. And so it would be something like this, where let me see if this is still going to, see if this will work. Yeah, so you'd have a mercury atom here bonded to a mercury atom here, and each one of these mercuries is +1, so the entire thing is +2. But these are bonded together because it's more stable together rather than alone. Whereas mercury 2 likes to be alone. Mercury 2 likes to be alone at 2+. Actually, if I scaled these correctly, mercury 1 should be bigger than mercury 2. Mercury 2 should be smaller. Each atom, that is. Okay. Am I missing something here? Chlorides, bromides, and iodides. What am I missing? Fluorides. What happened to fluorides? Is that a typo? Did I just forget it? And the answer is no, I didn't. It's purposely left off. And so why is fluoride not part of the table? Does somebody have an answer? So if I have a chloride, I have bromide, and I have iodide. I'll try to draw them with their respective size. Iodide is going to be the biggest. Chloride's the smallest. Where would you predict fluoride would be? Smaller than chloride. Fluoride's pretty small. Size does make a difference in chemical reactivity.
What's more reactive, bigger or smaller?
It depends on what you're trying to do. If you're trying to take electrons away, bigger is more reactive because it's easier to take electrons away from a big atom than a small atom. But what these are trying to do is they're trying to bond to a cation. And do we make a stable crystal lattice or not? And so we're going to have some cation here. Let's say I have a 2+ cation here. Which one of these four will form the strongest attraction to this 2+? Will it be the fluoride, the chloride, the bromide, or the iodide? The fluoride. Why? Well, being closer to the nucleus means it's smaller. So it's smaller. That's the reason why. But why being smaller would make it more reactive? And the reason is all these have the same charge. So if all these have the same charge, shouldn't they be equally as reactive? Because do you guys remember about electrostatic attractions in Chem 4, the two balls? In other words, with electrostatic attractions, opposite charges attract, however, like charges repel. And so all these are -1. Therefore, all these should have the same attraction for positive, shouldn't they?
Mass to charge ratio.
It's not the mass, it's the, but similar thinking. Not the mass, but it's the, well, it's also the distance, because if you remember Coulomb's law, it depends on the distance. The closer, the stronger. But it's the charge to what ratio? So if I look at this -1 charge, it's spread out over this big volume. However, if I look at this negative charge, it's concentrated in this small volume. So if we think about this, it's like your taste buds. You know, if you drink some lemonade, let's say you have some concentrated lemonade versus some watery lemonade that's been overly diluted. Which one's going to interact with your taste buds more strongly? The concentrated lemonade or the watery? The concentrated stuff. And so it's the same thing here. When we think about the negative charge, even though all these are -1, there's a difference in what we call the charge density, that is the charge to volume ratio. Here we have concentrated negative charge. This negative charge over here is spread out over a much bigger volume. Which one do you think is going to be more reactive? Which one's going to be more reactive is the fluoride. The fluoride is going to be more strongly attracted to this. And therefore, there are going to be a lot more exceptions here. These are solubility rules. All the rules have exceptions. We just don't want to memorize too many exceptions. So if you need to know what fluoride is, is it soluble or insoluble, it depends on case by case. And so what we do here is we can look it up. Like, for example, chloride, bromide, and iodide. Let's say this were calcium here. And then we say calcium chloride, it's too weak of an interaction. That is, the crystal will break apart. In other words, it's soluble. Calcium bromide, soluble. Calcium iodide, soluble. But what about calcium fluoride? Well, that's a bit more trickier because it might be a stronger ionic bond. The ionic bond, the stronger the ionic bond, that is, the stronger this attraction is, this electrostatic attraction, the less soluble and the higher the melting point. The less soluble because it's harder to break apart the lattice, and the higher the melting point is, it's harder to break the bond here. And so if we had something like calcium fluoride, then what we have to do is we have to do a little bit more work. And the bit more work involves, I'm just looking it up. So where would I start? I'd probably start here. Do you recognize this book? This book is called the CRC Handbook of Chemistry and Physics, and it has a whole bunch of data. This book is updated every year, so I don't know what edition we're at now. Actually, it probably says up here what edition we are. The 104th edition was 2023. So we're looking for the 105th edition. And this is updated every year because they want to make sure all the data is current and up to date. Here's an old edition, 1920 edition of it. This is the 64th edition. This book just gets heavier and heavier. The 64th edition weighs 6 pounds, 5 ounces. I don't know how many pages. God, a lot of pages. But you can look up the data there. But it costs money. The book is expensive. And they have an online version, which is also expensive. So we do the cheap version. The cheap version is going to be Wikipedia. So if we go to calcium fluoride, we can see here's the crystal lattice. How strong are these bonds? You know, which one? Is the white one calcium? Or is the yellow one calcium? How can you tell? Most of the time the anions are bigger. Most of the time. You'd expect calcium to be bigger than fluorine, but when you make the ions, the sizes flip. And it turns out that, if we look at our color coding system, you have to see. And so this could be fit because fluorides are actually quite small. That's what makes them so reactive, is their small size. So here I know which ones these are. Yeah, the fluorides are actually smaller than the cations, which is unusual. Because normally the anions are bigger and the cations are smaller. And so this is calcium fluoride here. This is calcium fluoride here. So the fluorides are smaller. So this must be the white, and the calciums must be the yellow in this case. But in the CRC, you'd see data like this. So you go to calcium fluoride, its molar mass is 78 grams per mole. Then we go down. The melting point's fairly high, meaning the bonds are pretty strong. 1418 degrees Celsius, pretty high. The solubility in water, 0.015 grams per liter. At 18 degrees C, at 20 degrees C, it's 0.016. The CRC would update it. It'd scan all the papers available and see if anybody has some more data that they could add to this. So, would you say that's more than 0.1 moles? 0.1 moles would be a tenth of that, would be 7.8 grams. Could we get 7.8 grams in a liter? If we get 7.8 grams in a liter, then that would be what we term slightly soluble because it's 0.1. If we can get less than 7.8 grams per liter, that would be insoluble, and more than 7.8 grams would be soluble. So what would we classify this as? insoluble. This is insoluble, but is it 100% insoluble? No, a little bit will dissolve. And our cutoff is totally arbitrary. I mean, 0.1 is actually quite a lot. And so we'll leave it there. It tells us that it's also insoluble in acetone, and it's slightly soluble in acid. So, some additional information there. And so in addition to the CRC, actually I'm going to copy that image here. There's another useful reference book. So this is the CRC handbook. This is from Wiki. There's another one that we often use, and it's called the Merck Index. Oops. The Merck Index has a bias towards biological and organics. Merck is a big drug company. Here's the 5th edition. We're well past the 15th edition here. So I'll just copy this image here. You can find a more recent edition in our library. Our library will have the Merck Index, as do all libraries. So again, the Merck is more for biological and organic, and the CRC has organics and some biologicals, but it's geared more towards inorganics. And then the low budget solution, which is just use Wikipedia. You know, Wikipedia is quite useful for looking up solubilities. All right. So our unknown dissolves in water. And what that's going to do is going to free up the sulfate. So we're going to get sulfate aqueous. Now we have translational motion and the sulfate's free to move, plus cations. We don't know what the cations are. And then there could be potential other anions, but we're not sure about the anions. But for sure there's got to be cations in there. Could one of those cations be calcium? Could our unknown contain calcium? And so what I'm asking is this. Well, I don't know. Let's take a look. And so after chlorides, bromides, and iodides, then what do we have? After chlorides, bromides, and iodides, then we look at sulfates. And sulfates are soluble except for which ones? Except for silver, lead, mercury, calcium, strontium, and barium. So these are the insoluble sulfates. All the other sulfates are soluble. So sulfates are mostly soluble, except when paired with these cations. Therefore, our unknown is water soluble. Since our unknown is water soluble, it means we cannot have these ions present. Otherwise, it would be insoluble. Otherwise, we'd have the headache. We'd be trying hot nitric acid or whatever to dissolve it, and it's not going to dissolve so easily. And so here, we can automatically eliminate lead, mercury 1, mercury 2, calcium, strontium, and barium in our unknown. We cannot have these in our unknown, otherwise it won't dissolve. However, silver might. The reason that silver might is because silver is slightly soluble rather than insoluble, and so it's borderline. Silver may or may not be present since it is borderline, and the borderline is 0.1.
So
It'd be SS, right? All the others would be I for insoluble.
And then, so let's say that we have water and we have an amount of sugar poured into hot water, and it'll be in solution for a while. But after like an hour or so, it'll fall out of solution. How do we define that?
Because temperature. Usually, if you have hot coffee,
Oh, so if it stays hot, it'll stay.
yeah, if it stays hot, it'll stay. Yeah, but as it cools down, it depends if you saturate your coffee with sugar. If you saturate it with sugar, then for sure, it'll as it cools down, it'll come out. Okay. Yeah. So.
If it stays hot, it'll stay in solution.
Yep.
Very interesting.
Yeah. If it stays hot, it'll stay in solution. So we can automatically, as far as the cations go, we know something about the cations. The cations cannot contain, well, they might contain silver, but they cannot contain lead, mercury 1 and mercury 2, calcium, strontium, barium. Otherwise, they can be anything. All right, let's finish up this table since we started it. Okay, number 5, what do you look at next? You look at hydroxides next. Hydroxides are mostly insoluble, except for group 1, ammonium, and calcium, strontium, and barium. So hydroxides are insoluble except for group 1, ammonium, calcium, strontium, barium, which are soluble hydroxides. And then after the hydroxides comes sulfides. Sulfides are insoluble except when paired with these. Group 1, ammonium. Let me do the hat. And group 2.
We're not gonna memorize these, right? Like in full detail.
You should memorize these. Yeah, there's a lot of memorization, fortunately. You should memorize these. But, you know, to help aid yourself to lighten the memorization load, we try to memorize these in a different way as well. All right, after sulfides comes, yeah, phosphates. We'll do carbonates and chromates, which are insoluble except group 1 and ammonium. You might think, why bother memorizing these? You can always look it up, right? I told you how to look it up, CRC, Merck Index, Wikipedia. Always look it up. But, you know, what we're trying to get is we're trying to gain a better understanding of chemistry. In order to gain a better understanding of chemistry, we want to see, you know, the patterns or the rules or the laws of nature, you know, how nature behaves. And so there's certain things that we might consider. It's calcium, strontium, and barium. What happened to beryllium and magnesium? If you look at group 2 starts off with beryllium, magnesium, calcium, strontium, barium. What happened to beryllium and magnesium? Too small. Too small meaning too reactive. Right? In fact, beryllium, you don't want to deal with beryllium. Beryllium metal was used in aerospace here in the South Bay for many years. And so people would machine beryllium like magnesium. You know, they machine magnesium's lightweight, beryllium's even lighter. Magnesium's good, strong structural metal. Beryllium is also a good, strong structural metal that's extremely light in weight. But the problem with beryllium is this. If you ingest beryllium and you create beryllium ions, the beryllium ions will substitute for magnesium and calcium ions in your body. And we need magnesium and calcium for things to function properly, but if beryllium gets in there, it's too reactive. And it screws up. And so the people who used to machine beryllium here in the South Bay all ended up dying prematurely. And they didn't die right away. It took years. You know, it took decades for some, but eventually they developed, I forgot what it was, cancer or something, due to beryllium poisoning. And so we don't want to deal with beryllium. But magnesium's fine. You know, there are people who take magnesium supplements all the time. People who soak their feet in magnesium baths with magnesium ion. And so magnesium is like a muscle relaxant or something. I think that's what it says on the bottle. But why isn't magnesium here? Well, it's too small too, and so there are too many exceptions. So if you're looking for magnesium, you've got to look it up. And so when we look at this, the mostly insoluble ones are going to be like high charge density. Hydroxides are small. Hydroxide is just an oxygen with a hydrogen. Hydrogens are tiny. Whereas sulfate, you know, even though hydroxide is a -1, sulfate's a -2, but it's a lot bigger because you got a sulfur with how many oxygens around it? 4 oxygens. So it's kind of a big ion. So sulfate's big even though it's a -2. And that means the sulfates are mostly soluble. These are kind of big with low charge. These are even bigger with low charge. However, when we get to sulfides, those are getting smaller with higher charge. And then look at these. Phosphate, what's the charge on phosphate? 3 minus. Carbonate, 2 minus. Chromates, 2 minus. These are high charge and small. These high charge and small are fairly reactive. And therefore, they're going to form stable precipitates or stable solids. Fairly reactive is reactive with the cations. That's what I'm talking about. With cations to form a precipitate. And so there's certain things that can help you. You know, so if you forget the solubility rules verbatim, then you can just kind of go off that, you know, the trends in the solubility rules. That's what we do. How about sodium ions? Are sodium ions very reactive? That is group 1. Will sodium ions react with sulfate? And the answer is no. The sodium ions won't. But we can form sodium sulfate. Let's say the cation we have here and here is sodium ion. It's like this. It's like two fishes. You know, if two fishes are swimming in a pond, they're going to stay away from each other for as long as possible. But what happens if you keep evaporating the water in the pond? And so the pond gets smaller and smaller and smaller. And pretty soon the two fishes can't avoid each other. And pretty soon, let's say all the water evaporates and the two fishes are going to be together. That's like sodium and sulfate. We can put sodium and sulfate and we can precipitate those out, but the only way to precipitate those out is to get rid of all the water. And if you get rid of all the water, then the sodiums will be forced to precipitate out with the sulfate. And so it's kind of the last resort. However, there are some cations that absolutely love sulfate. What cations like sulfate that will react with sulfate? In other words, this is what's going to happen. We don't have to get rid of the water. If this cation comes into contact with a sulfate, they stick together. If they stick together, then eventually they'll form a crystal, because we have more ions stuck together, we'll get a crystal, and that crystal will form a precipitate. And so what cations like sulfate, like to react with sulfate? Calcium? Yeah, calcium likes sulfate. Any others? What else? Calcium, strontium, barium. What else? Silver, lead, mercury, calcium, strontium, barium. So we kind of memorize it like that because it fits sort of a pattern. So silver is kind of borderline. We're not going to use silver. We could use lead. And we can, if we put in lead ions in here, the lead ions and sulfate ions will immediately come together and form a precipitate. Lead-2 sulfate. Lead-2 sulfate is a nice white precipitate. Lead-2 sulfate was the white pigment in paint in the old days. But we're not going to use a lead because of its toxicity. We're going to stay away from lead. Mercury, same thing. We don't want to use mercury. Calcium would be good because of its fairly low toxicity. Calcium would be good. Strontium we don't want to use because there's a lot of radioactive strontium mixed in with our normal strontium. You know, all the nuclear tests, you know, above ground nuclear tests, and then I don't know, Chernobyl. For sure, Fukushima released a lot of radioactive strontium. So we're not going to do it. Our strontium, if you bring a Geiger counter, our bottles of strontium are radioactive. Barium's okay, except barium, if you look at its position in the periodic table, it's down low. And some of the barium is kind of a heavy metal. You know, the heavy metals are down low. Although cesium we wouldn't consider a heavy metal, slightly, but barium, yeah. And so there's like lead and mercury. Barium is a heavy metal. We want to avoid contact. And so barium chloride is poisonous. And so we got to watch out. And so what I'm going to do here is this. There are other things that like barium too. And these other things that like barium, we're going to add some acid. And the acid we're going to add here is hydrochloric acid. The reason we're adding the hydrochloric acid is not to dissolve our unknown. The reason we're adding the hydrochloric acid is to prevent interfering precipitates. So the purpose of adding the hydrochloric acid is to prevent interfering precipitates. Because there are other things that like sulfate ions. And there are other things that like barium ions. The other things that like sulfate ions, we just don't add those. But we're going to add barium chloride. And barium chloride is going to contain barium ions, aqueous. And what's going to happen is the sulfate ions and the barium ions are going to come together and react to form a precipitate. And so we end up forming little crystals of barium sulfate. And we're going to get so many crystals of barium sulfate, this turns cloudy white precipitate. Although I made it green. What other ions like barium? Can you think of any other ions that like barium? How about sulfide? No, not sulfide because group 2. Did I do sulfides? Yeah. Not sulfides because group 2 and sulfides are soluble. So they're going to stay away from each other unless you evaporate all the water. But phosphates, carbonates, and chromates do like barium. So if I have phosphates, carbonates, and chromates present in my unknown, I'm going to precipitate out barium carbonate, barium phosphate, and barium chromate. But to prevent this, I add the HCl. What happens is the HCl will eat up the carbonates, phosphates, and chromates. And it prevents these interfering precipitates from forming. However, barium sulfate, barium chloride is quite toxic, but did you know I had to drink barium sulfate? This is toxic. I had to drink barium sulfate because I went in for a CAT scan, and barium being a heavy metals love to eat up X-rays. And so, barium sulfate is an imaging agent. But what I drank was something like you're going to make today. It was like a cloudy, white suspension. And what it tasted like somebody had crushed chalkboard chalk and mixed it with water and left a really chalky taste in your mouth. But it was good at imaging X-rays, so it did that. And so barium sulfate is generally regarded as safe because this is insoluble in your stomach acid. And the barium ions are locked in the lattice. It's the barium ions that are going to give you trouble. Whereas in barium chloride, this is soluble. soluble salts are strong electrolytes. Strong electrolytes are going to ionize or dissociate in water, so it's going to have free barium ions. The free barium ions can go ahead and try to replace for calcium and magnesium in your body and cause trouble. These crystals are tiny, and what we end up with is a colloidal suspension. Colloidal suspension have particles that are so tiny they stay permanently suspended. You know, when we have particles, they should settle down. The precipitate should settle down to the bottom of the beaker, but they never do because these crystals are too tiny. It's like milk. You know, if you wait for the proteins in milk to settle down, you're going to be waiting forever because milk is a colloidal suspension. The particles are too small to settle down. But what we're going to do is we're going to try to coagulate our colloidal suspension. And so we need to coagulate by doing this. Do you know what this symbol stands for? Heat up, yeah. Let me heat this. And what happens is when you heat it, you're increasing the kinetic energy, and you're going to get these colloidal particles to collide and stick together. Now, this is really like two little clay balls, and you throw them at each other, they'll collide and stick together. And so what we want to do is we want to coagulate this to generate bigger clusters of crystals, and those bigger clusters of crystals, once they get heavy enough, they'll fall down to the bottom. And so we'll coagulate this and then clear up the solution. Yeah. We have to heat it up because what happens with these colloids is, and you could read about this here. This would be like, you know, these tiny crystals sometimes build up surface charge. And if they build up the same surface charge, that is, let's say we got anions stuck on the outside here. Those are more prominent. Then these light charges repel, and so it keeps the particles apart. By heating this up, we can force them to collide. And when they are forced to collide, then the positives can better interact with the negatives and cause these particles to stick together. And that's the coagulation process. And so how do we coagulate? The way we coagulate it is we just heat it to boiling. That should be enough. You heat it to boiling, it coagulates a little bit, and then set it aside. So what I do is if I have a cloudy white suspension, and it's so cloudy I can't see anything going on there, I'll heat it up to boiling and then take it off, let it settle, and then I'll be able to see two layers. The precipitate layer on the bottom and the solution layer on top. So something like this. Okay, once it's cleared up, then I can test because I don't want to leave any sulfate behind in solution. What I'm trying to do is I'm trying to capture all the sulfate. And so all the sulfate, you know, essentially we're doing this. What we want to do is we want to release all the sulfate from the unknown solid by dissolving it. Once all that sulfate's released and free, then we want to capture all that sulfate by precipitating it out with barium. And so what we have to do is we have to make sure that there's no sulfate left behind in solution, that we've captured all the sulfate. And the way we're going to check that is we're going to add another drop, or multiple drops of barium chloride. And so I'll get a dropper bottle, and then I'm going to try to add some drops of barium chloride and keep an eye on this. So here, a drop comes down and splashes on the surface, and then I want to watch this drop sink. as I watch the drops sink, I want to see if additional cloud formation appears. So two things can happen. One, I get additional cloud formation. If I get additional cloud formation, then I'm not done. I haven't captured all the sulfate, and so what I need to do is I need to keep adding this until I stop seeing cloud formation. If it gets too cloudy, then I'm going to coagulate it, and then cool it, and then check it again. And so just repeat the coagulation, cooling. And then what we want is we want to add drops, and usually I drop like 3 or 4 drops in different areas here, and then watch it sink. The barium chloride is more dense, so it'll sink in the water. And then eventually mix. But I want to watch that drop, and if I see no cloud formation all the way to the bottom, then I'm finished. Sometimes what happens is it'll get halfway down, and then you get cloud formation. Then you have to keep going. But once we're done with this, then I might try to coagulate it one more time, and then cool it, and then put it in the drawer. Because I know it says to heat it for 1 hour. You don't have to heat it for 1 hour. We just get it to boiling, and then we're going to leave it in our drawers overnight. And so if this is done, then I'm going to let it cool down a little bit, cover it with a watch glass so nothing falls in, and then put it in my equipment drawer. I'm going to collect them next time. Or put them in the cabinet over here if you don't have enough room in your equipment drawer. This is a multi-day experiment, so this is as far as we're going to get today. All right, now there's other complications that I want to talk about. The first complication is this. You know, these ionic lattices have charges, and water is polar, and so water is going to be attracted to these charges, either the positive or negative. And so what can happen is water can attach to the surface of the crystals. Sometimes the water molecules can wiggle inside the crystals. So if you have a crystal lattice, there's a maze of passages in there called void spaces, and the water sometimes can wiggle inside those passages and create a hydrate. Hydrates have water molecules that have wiggled their way inside the crystal lattice. And so we don't know how many waters wiggled their way in, and we don't know how many waters are stuck on the surface of the crystal. And so what we need to do is we need to dry the unknown in an oven. And so this was done before lab today. They came in and dried these overnight in the oven. All right, so before lab, somebody came here, dried this. And then if the experiment is complex, what I'd like to do is I'd like to sketch out a schematic drawing of the procedure itself. Because I don't like to read the procedure in the lab manual. When I read the procedure in the lab manual, it's too much. Like, for example, procedure: obtain the dried unknown in weighing bottle from the oven. Well, those are going to be passed out. And then reading this, look at this procedure. Do you want to read this? So if you don't like drawing little schematic diagrams, then what you can do is you probably can summarize this entire paragraph into one sentence. And that's very helpful because as you continue in labs, some of the labs are too much work for too little time. This is not the case for this one. If you wanted to read this carefully, you can. But when I was a student at UCLA, most of the labs you didn't have enough time to finish, and just barely finish. Sometimes you're all right, but one way to make sure you finish is to prep your lab notebook before. And so the pre-lab work I do is not the pre-lab quiz, it's not the pre-lab questions, but it's the pre-lab notebook prep. For the pre-lab notebook prep, I need to know how much sample I need. Do you know how much sample do you need? Am I on procedure 1B or procedure 2? Let me make sure. This morning they told me a different amount. Add between 0.15 and 0.17 grams of unknown sample to the beakers. Dissolve each sample in dilute HCl. We don't need the HCl to dissolve it because they're water soluble. Put barium chloride, 10 milliliters. And so what I do is this. I go through the procedure and then just on my drawing, this is what I have in my lab notebook, is something like this. Somebody told me 0.3 to 0.4. Double check this.
I think there are two different instructions.
Yeah, two different ones. We're on the second set. Is the second set 0.3 to 0.4?
Yeah.
Okay, then I'm wrong here. If I make a mistake, I just do this. And then what I do is I do the procedure out. How much water? How many milliliters of water did it say to add?
50 milliliters.
50 milliliters. And how much HCl?
2 milliliters of 6 molar.
2 milliliters of 6 molar. And then how much barium chloride?
10 milliliters of 0.25 mol.
Yeah. That's what we call procedure. Let's say the procedure is to run on the treadmill for 2 hours, but let's say you only ran for 10 minutes. So the procedure might have said one thing, but what you actually did is something different. And so what I usually do is write in a different color ink. I'll write how much. So let's say I accidentally overshot this. I got 0.4115 grams. Is that a big deal to overshoot it? No. If I overshot it a little bit, it's not a big deal. If I overshoot it by a lot, then it's a problem, because then we have to adjust the amounts more significantly, but that's okay. So if you're over a bit, like say if you go over 0.5 grams, I'd probably get rid of some. Now weighing this isn't going to be as easy as some of the other stuff is to weigh, because one, the reason we heat this up is to drive off any surface water or water trapped in the maze of the crystal lattice. But what happens when this cools down? It's going to reabsorb it, because this is humid air. This is what, 20–30% humidity, something like that. And so if this cools down, the surface water will reabsorb, and then water will work its way back into the crystal, create a hydrate. And so what we have to do is we have to protect this from reabsorbing water. Now this is a special bottle. This is called a weighing bottle. And a weighing bottle, do you see the top here? That's machined. This is called ground glass. And we have a ground glass here, and this is called a ground glass joint. It's a very tight joint. In fact, it could get stuck. And so what we're going to do, and we have enough desiccators, is we're going to cool down. We're going to cool down, actually I'm going to cool down the whole thing. So you're going to get something like this in a beaker, like this, and a tray. This is going to be too hot to touch. And we have something called beaker tongs. Let me show you what beaker tongs look like. We have a box of beaker tongs over there. And so you can grab a pair of beaker tongs. And beaker tongs are meant for gripping beakers, so we can hold the beakers quite easily with beaker tongs. But anyway, this is probably going to be too hot to touch. You can use paper towel to grab it if you need. But these are beaker tongs. Beaker tongs, and what are the other tongs you have? Crucible tongs. This. So I set everything up. This is going to be hot. This is fine. If it's hot, the water is not going to reabsorb. Now this is ground glass joint here. But it's flat. And you see the lid doesn't fall off. The lid doesn't fall off because it's a greased ground glass joint. So if I want to remove the lid, I can't pull it off. Watch. If I try to pull it off, do you see it doesn't come off? And so what I'm going to do is I have to push it off to the side like this. Okay, and then it'll come off. And then what I'm going to do is I'm going to let it cool in this thing. You know what this thing's called? A desiccator. And so I'll just grab these with a tong. Hopefully these aren't too rusty and a rust chip doesn't fall in there. So I'll cool this off in here and then just replace the lid. It says to leave the lid ajar for 10 minutes. I don't do that. You're only cooling one sample. The reason it says to leave the lid ajar is because as this cools, the hot air will contract. The volume will contract and create a vacuum. If this creates a vacuum, it's hard to break. But you don't have to worry about that. I'd rather not leave this open for 10 minutes because then too much humid air will get in there and it takes extra time to desiccate that humid air. The desiccant is this blue stuff on the bottom. When it's blue, it's good. It'll absorb water. When it turns pink, you see some pink ones there? Those are bad. Those have already absorbed the water. And so the color changes depending on how much water those have absorbed. And so we'll let this cool down. Okay, once this is cooled down a little bit, it doesn't take that much time. You know, it could still be warm. I'm going to take this out and then cover it like this. I can handle this with my fingers. The reason I can handle this with my fingers is I'm not going to weigh this. It says to weigh the weighing bottle. Don't bother weighing the weighing bottle. We don't need to know how much it weighs. Also, don't bother weighing the beaker. We don't need to know how much it weighs. What we're going to do is we're going to put the beaker on our balance and then tare it, that is zero it. And then what I'm going to do is I'm going to tap some of this in here. So let me break this apart. And then what you're going to do is, this you'll have to twist open. Sometimes this lid, is very tightly sealed. You want to keep this open at a minimum time and then just tap some sample into the beaker. Actually, the beaker is going to be like this. Just gently tap it in. Hopefully you don't overshoot. If you overshoot, you might have to tap some back. And then you're going to weigh out anywhere between 0.3 and 0.4. It doesn't have to be exact. It's just going to be close. All right. Is that good? There. We don't have enough equipment. So what you're going to do is you're going to work in a group of 3 or 2. And each one of you will do 1 beaker. And so what we have to do is we're going to have to divide this up. I think we have enough for 4. So if there's a group of 4, we might be able to do it with the same sample and not run out. We might run out though. All right, so once you have this, then we add our water, our hydrochloric acid, and our barium chloride, and then heat it up. We heat it up to coagulate it. So go ahead and turn on the hot plates now to 10. They take some time to warm up. So let me talk about safety now. The unknown sample, those at least those don't contain the heavy metals, those ones, and probably it's just some innocuous sulfate salts or salts. But the hydrochloric acid we got to worry about. Hydrochloric acid, what happens if you splash some in your eyes? Let's say some gets underneath your goggles, gets in your eyes. If you get hydrochloric acid in your eyes, it's going to sting a lot. If it stings a lot, you probably can't see because you're going to be clenching your eyelids pretty tightly. And so if you see somebody with hydrochloric acid in their eyes and they're in pain or something like that, then help them. Help them to the eye wash fountain. Do you know where the eye wash fountain is? We have one here, but this one's kind of far. This one has 4, and then there's no drain. This drains just on the floor. So if possible, use the eye wash fountains at your sink. Do you see the eye wash fountain at your sink? So you could use those, except if the caps are off, or even if the caps are on, you want to just spray a little bit to wash anything that got stuck in there off first, and then hit your eyes. And so go to the sink and use the eye wash fountains. And then how long do you need to rinse for? 15 minutes. And why so long? Because after a minute, your eyes will start feeling a lot better. But the reason they say 15 minutes is because it's going to seem like forever. 15 minutes at an eye wash fountain is going to seem like a long time. It's going to be painful. It's like torture. But they say 15 minutes because it's like trying to wash a wet sponge. You know, let's say you spilled some hydrochloric acid on a wet sponge. You know, you might wash the surface off immediately, but, you know, the stuff that gets absorbed in there is more difficult to wash out. And so wash for 15 minutes. Let's say if you spill some on your arm, then you want to wash with soap and water. Usually that works good. And rinse. You might rinse for 15 minutes, but I've spilled lots of hydrochloric acid on my hands and arms. It wasn't so bad. Not this stuff, because this stuff, 6 molar, we call dilute. If it was the 12 molar stuff, then I'd probably spend a lot more time washing it off. What happens if you spill the whole bottle onto your clothing? What should you do? Let's say your clothes are saturated with hydrochloric acid or something else. What should you do? You should immediately rinse it off. So you could use the handheld. You can pull those out. They have a pretty long hose. You could use the handheld to rinse it off, or you can come over here to use the safety shower. You know, and pull down the handle. It'll be drenched with water. But it's still the same thing. If it gets soaked into your clothing, then it's like a wet sponge. How long do you have to wash that off before you get it out of your clothing? A long time. So this is why they recommend, you've probably seen the safety video where they recommend that you strip off all your clothes so that you can get the contaminant off your skin. It's happened before. It happened before where, not hydrochloric, but it happened before where a student had concentrated sulfuric acid spill onto their jeans. And it was burning. So you can wash it off your jeans, but you're washing it off the surface of your jeans, and it's going to take time to wash off, right? But they didn't, of course they didn't want to take off their pants in the middle of the lab. And so they went into the restroom. But, you know, by the time, the restroom, they're trying to wash it off at the sink, it wasn't very effective. And by that time they got burns, like 2nd degree burns. Concentrated sulfuric can give 3rd degree burns. And they're like just regular heat burns. Since that accident happened, we have this. So initially, if you spill something, you could do this. This is the public shower, but we have a private shower. The private shower is located behind the lecture room. And so there, you know, you get most of it off here, and then you can go over there and make sure it's off completely. The acid, that is, off completely off your clothes and your body. Okay. Or whatever other contaminant that we have. Like I said, barium chloride is toxic, so avoid contact with that. You know, barium is can screw with your magnesium and calcium. Barium sulfate's not so toxic. I had to drink this stuff. I didn't die. And barium sulfate's generally regarded as safe. But don't touch it. You know, and try to not to handle it too much. All right, any questions? Okay, what a lot of people do is when they're in the weighing room, I see this all the time, they just leave the lid off. Do you want to leave the lid off for a long time in the weighing room? No. You always replace it. The other thing is you could bring the desiccator in if you're really, but you're probably okay, just replace the lid after you weigh it, because these are not that, they don't pick up that much water, these salts here. But just make sure between weighings. Now, each of you will weigh your own sample. So once one person's done, pass it to the next person in your group. All right. Well, I guess that's it then. Just go ahead and get started. You'll have to go to the stock room here to get your sample. You'll need a pair of beaker tongs from that wood box over there. Just one beaker tong per group is probably enough, or two. And let me see if I can get the stock room.